Hello, everyone. Today, I'm going to talk about my recent work with Srinivasan Arunachalam, and this is about memoryless communication complexity. Uh, so before I begin explaining memoryless communication complexity, let us quickly recap what a standard communication complexity is. Standard communication complexity was introduced by Yao in 1979, and it looks like this. Here we have two players, Alice and Bob, and they receive their private inputs, X and Y, which are n-bit strings each. And using that, they want to jointly compute a function f of x, y. It's a binary valued function, and they're interested in knowing only the function value. Now, obviously, in order to compute this, compute the function value, they need to communicate. So they communicate back and forth by sending bits, by sending one bit at a time. And here we assume that the players are not limited by any computational time or memory. In other words, they can compute locally, they can compute any functions they like, and they can also remember all the message transcript that they have received or sent previously. Now, a cost of any communication complexity protocol is the total number of bits exchanged between Alice and Bob for the worst possible input. So we want to optimize on the number of bits sent for computing any function. So we defined deterministic communication complexity to be the minimum over all the protocols computing the function. So it is denoted by D of f, and it is the cost of best deterministic protocol computing the function f. People also consider another setting of communication complexity, which is one-way communication complexity. Here, everything is same, except the fact that now only Alice is allowed to send messages to Bob. So here, the cost of any one-way communication complexity protocol is the total number of bits sent from Alice to Bob. And after receiving all the bits from Alice, Bob computes the function value, which is either 0 or 1. Now, we ask this question, what if the players have no memory in between the rounds? Now, let me explain what I mean by that. We say that at every round, so we want that Alice computes the next message to send. So this is going to be solely based on her input X and the message she has received from Bob in this round. And similarly for Bob. So Bob is going to compute any message that Bob wants to send in any round that will be based solely on his input Y and the message received in this current round. So let me further elaborate with this pictorial representation. Here we again have Alice and Bob, and they have their input X and Y. And since they don't have any memory, and they don't even have memory to remember in which round they are currently in. So Alice begins, and in using her input X, Alice chooses a function f of x, which she initially applies on all 0 string, and she computes the first message to send, which is MA1. Now, Bob receives the message MA1, and based on his input Y, chooses a function fy, and he maps MAI to another message MBI and sends it to Alice, and then forgets about it. And similarly, this keeps on going, and obviously at some point we need to stop. So we denote it by saying that if ever any player receives a message which looks like something like this, where it is all zeros except the last bit is B, then the output B. Now, any protocol computes a function this way if it computes f of x, y for all possible x and y. Now, it is easy to see that via a counting argument that if we have this message to be only a single bit, then it doesn't suffice to compute all possible functions. So here we need to have this message to have like length more than one for computing any non-trivial functions. So we define the cost of computing such function in this model is the size of the largest message communicated between Alice and Bob in any round of the protocol. So it is really the bottleneck size of the message that they need to send back and forth. So let me tell a story which fits this model really well. So intuitively, it is basically sending a rewritable message register that they can send back and forth to compute the function f on all possible inputs. Um, so we have these two players, Alice and Bob, and they have their private inputs. So they remember their private inputs, and with that they want to solve a mystery, which is basically computing f of xy. Now, as the story goes, they cannot remember things for too long. So when they go to bed, they wake up the next day and they cannot remember anything from the previous day. To make the matter worse, they're also separated by space. So they're on two stranded islands, and it takes few days to send message from one player to the other. And with that, they want to solve a mystery. So they decided to use a postal service, and they decided to write notes and send back and forth. So they can basically send notes using this postal service. But obviously, they want to optimize on the size of the envelope. So they want to buy the smaller envelope possible in order to accomplish this task. And that is exactly this memoryless model. And we want to optimize on the message register. Now, we can also have variants of memoryless communication complexity model. So note that we are still computing the same function, distributed function, but we can have this table where we can say that the memoryless model is where neither Alice nor Bob have any memory. We denote it by nm of f, which is abbreviation of no memory. And this is the complexity of computing any functions in the memoryless model. But then we can also have a model which is memory no memory, where one player has memory and the second player doesn't have any memory. So we denote it by m of f, which is memory no memory model. And it actually turns out that any functions in this model can be computed with at most log n size message. And the reason is that here the player with the memory can just send an index to it's actually log n plus 1. So the player can just send an index to the other player, and then the other player can just reply. So the player can send I, and the other player, Bob, for instance, can reply with yi. And that way, Alice would retrieve Bob's whole input. The third variant is where it's a memory model, where Alice and Bob both have memory. And then this becomes the standard communication complexity protocol. So here it's denoted by D of F. But note that we can also have one-way variant of all these different variants. So we can have one-way communication complexity, but in the memoryless setting. So Alice and Bob do not have memory, and furthermore, communication only goes from Alice to Bob. We denote it by nm superscript right arrow of f. And it turns out to be standard one-way communication complexity, because it just, since neither has memory, it just makes sense to send just one message just in one shot. And then we can also have memory no memory in the one-way setting, and we denote it by m superscript right arrow f. And this is exactly a model which was actually studied in 2014 by Papa Constantiniu and others. And yeah, so we can have all such different variants in the by choosing like whether Alice and Bob can have memory or not. Okay, note this inequalities relation between this all different variants of the model. So it is not very difficult to see that this set of inequalities hold for all functions. And in fact, all these inequalities are actually exponentially weaker. So in the sense that there exists a function, explicit functions for which this model is, the complexity in this model is exponentially better than this one. And similarly, there exists a function for which this is exponentially better than the one, and similarly here. Okay, so a quick recap, like we have these two players, Alice and Bob, and instead of having standard communication complexity, we can have, we can choose to have whether they have memory or not, and whether the communication is two-way versus one-way, and we can have all these different variants of communication complexity model. Now, we would like to see how it fits with other space-bounded model that have been already studied. So here I'm gonna describe three different space-bounded models, and then we will see how they're connected to our newly defined model. So first of all, it's a garden hose model. It was introduced by Burman and others in 2013. And this is really a playful definition of communication complexity model, where Alice and Bob, they have their input X and Y, but they're actually neighbors, and they share a few pipes which are going across the boundary of their gardens. And based on their private inputs, Alice also has, they also have some of the hoses. So Alice makes some of the connections. Alice puts some of the, matches some of the openings on her side. Bob also matches some of the openings on his side, and they cannot see their connections so they can only see their connections on their respective side. And Alice also connects a tap to one of the pipes based on her input. Now, obviously, if since it's a matching of the pipes, and if Alice starts a flow, then water would eventually go back and forth through these pipes based on the connections, and it will eventually spill on one side. And in this case, we are seeing that it actually spills on Bob's side. So we can define that if water ever spills on Bob's side, the function value would be 1. If it spills on Alice's side, the function value would be 0. Then we can say that this way we can compute a function, and it turns out that we can compute any functions using such setting. And the complexity is basically how many pipes we need in order to compute a function f for all possible x and y, and the number of pipes is basically the complexity in this model. Second space-bounded variants that we know of was defined by Brody et al. In 2013. So in this model, Alice and Bob, they are limited memory-wise in the sense that they don't have unlimited memory, but rather they have Sn amount of memory. So both players have Sn amount of memory. So it's similar to our model here. They don't have any clock to remember like which round they are in. If they want to remember in which round they're in, they need to store it in this space. And again, here they send bits back and forth. So instead of unlike our model where the players exchange a message register, here this sends bits back and forth, and they just update their private SN bits register, and they compute a function in this way. And the cost of computing a function is basically the size of such register. And then the third variant is overlay communication complexity. So this was, so I've already mentioned that this was introduced in 2014 by Papa Constantiniu. And this is exactly a setting where Alice has unlimited amount of memory, but Bob doesn't have any memory at all. So Bob doesn't know in which round, Bob doesn't even know in which round he is in. Bob just receives a message. So now the message could be a multi-string message, so at any round. And Bob receives a message, and Bob can either output 0 or 1, or he can continue. And the goal is to compute a function this way. And they have shown that this model is characterized by this really beautiful combinatorial object called overlay. So in normal communication complexity, we have a rectangle which gets partitioned into smaller rectangles, but here it is an array of rectangles, an overlay of rectangles, and the main rectangle gets covered by this array of rectangles, and any particular point x and y gets the value of the first rectangle that it encounters. Okay, so having explained these three things to three different models, let me tell you like how they are related to our setting. So as I've mentioned, I mean, this is exactly the setting. So this is exactly it turns out to be one of the setting that we consider, but so we don't claim it to do it ourselves, because this is already done in this work. It just turns out that when we set like our models this way in this particular setting, it turns out to be the exactly the overlay communication complexity. But let us see like how space bounded the model is related to our setting. Now, from these two pictures here, this is the space bounded model. This is our model. You can already see that these two things are almost the same, because here they exchange message and then the update register. Here they exchange, they send the message register back and forth. So these two actually, it actually turns out to be same. So it's not very hard to see that if we define complexity in this model to be Sm of f for computing any function, then memoryless communication complexity is actually upper bounded by 2 times Sm of f plus 1. And Sm of f is also upper bounded by memoryless communication complexity plus log of memoryless communication complexity. So these two models are exactly like linearly related. Now, we want to connect it to Gardner's model. So, but there is a claim from Brody et al. Paper in 2013 that Gardner's complexity is actually related to the space-bounded communication complexity that they defined in this manner. So using this and the relation that we have in the previous slide, it already immediately follows that Gardner's complexity and our defined model of memoryless communication complexity is factor 3 related. But it turns out that we can actually tighten this bound, and we can show that memoryless communication complexity is actually similar to log of Gardner's complexity. So it's actually lower bounded by log of Gardner's complexity minus 4 and upper bounded by log of Gardner's complexity. So in other words, these two models are exactly the same. Now, one advantage of having this model, the memoryless communication complexity, is that now we can look at all the Gardner's protocol, or for instance, the space-bounded model in terms of non-deterministic, in terms of memoryless communication complexity, and study it there. So this is one of the consequences of this tight relation that we have obtained, which is about indirect storage access. Now, indirect storage access function, which is defined this way, it is essentially x of y of z. So we are given this indirect storage access functions where it is a n-bit string to 1-bit string function. But the function is defined this way. This input is interpreted as this. So we have a vector x. We also have a bunch of vectors y's, yi's, and we also have z. And the way to evaluate this function is, first of all, z, the integer value of z, points to one of the location of y. And that particular y that we obtain, that points to one of the location of x. And then we look at that particular location and we look at whether it's 0 or 1, and that's essentially the output. So that's why it's like it's called indirect storage access. And in order to turn it into a distributed problem, we can give Alice x and z, and we can give all the y's to Bob. And you can see that this is hard for a single player to compute the values, so they need to communicate. And this y's do not have to be unique. So because of that, it seems like in order to compute this function in the Gardner's model, it requires omega n square many pipes. And that's why it was conjectured by Clark and SP in 2014 that indirect storage access function actually requires omega n square. But using this new characterization, I mean, new connection that we have obtained via this memoryless communication complexity, we can see that this conjecture is false, and we can actually get a protocol which is linear in N. And this turns out to be very easy protocol, because in the memoryless protocol, it is very easy, because Alice just can send Z to Bob, and then Bob can just compute y of Z and send it back to Alice, and then finally Alice can compute the answer. So here, the way the function is this is defined, this y's could be at most log n bits, and that's why the complexity is log n. And since it is log n, if we translate it back to the Gardner's model, we get a protocol which is 16 times n. So this is linear. So as we are seeing that this is already a novelty of this model, that we can use this new framework to study Gardner's model. We can also show that, so here I'm not mentioning it in the slide, but we can also say something non-trivial about space-bounded model. There we can say that some of the things which looks easy in space-bounded model, it actually, in using this framework, we can actually see that that's actually hard. So it makes, this model makes things clear to see. Okay, so far we have this, we have established this following inequality relating all this different models. So now we see that, okay, these three models are actually equal, and they sits in between this models. Now, see, another advantage is that since log of Gardner's is upper bounded by m one way of f, meaning we can use overlay complexity to design a protocol for Gardner's. So that gives us another way for designing a protocol for Gardner's as well. And we have explored this direction, and that also turns out to be fruitful. And um, uh, it happens that for this problem, disjointness with quadratic universe, it was conjectured to have, again, like quadratic complexity in like omega and m square complexity in Gardner's model. But using a protocol in this model, we see that we can actually slightly reduce it to m square over log square m. So, so perhaps we can say that the memoryless communication complexity framework and its variants are cleaner framework for studying all these three previous space-bounded communication complexity models. Now, so here, I have already mentioned that for the overlay complexity, there is this really nice characterization of overlay complexity. So then the question is, can we also do the same for memoryless communication complexity? Can we come up with a characterization, like what is happening in terms of partition when we talk about memoryless communication complexity? And it turns out that memoryless communication complexity is actually characterized by bipartite branching program. So that's also another connection with another complexity theory theoretic model, which is branching program. So before I explain what is a bipartite branching program, let me quickly tell you like what is a branching program. So branching programs have a starting node and two sync nodes labeled with 0 and 1, and sync nodes do not have any out degree, and the starting node doesn't have any in degree, and every other node and has including this node has out degree 2, at most out degree 2, and they're labeled by variables of the form xi. Now the way it works is that whenever we get an input x from like x0 to xn minus 1, that sets that activates one of the paths and deactivate the other one. And based on that, for any particular x starting from the starting node, we can traverse the graph and then reach either the 0 node or the 1 node. And then we say that a branching program computes a function f if for all the 1 input, starting from the starting node, we reach the 1 node, and for the 0 inputs, we reach the 0 node. And then the complexity of branching program is denoted to be the smallest such branching program computing f for all possible x. Now we can also have bipartite branching program. Now in bipartite branching program, it is exactly the same scenario, but now all the nodes, instead of getting denoted by all the variables xi's, now they are either denoted by a function fi coming from this function family curly f, or denoted by gz coming from this function family g. Now, what is happening here is that at each node, we can compute any function based on either x or either y, but not both. And again, the out degree is 2. So again, the goal is the same, like starting from the starting node, we want to reach either 0 or 1. So this branching program, since it's bipartite in nature, it is capable of computing a bipartite function, which is like f of x and y, and it outputs a Boolean value. We can also have a generalized version of bipartite branching program. So here the differences from the bipartite branching program is that it is exactly the same scenario, but now instead of having degree 2, here we can have more than degree 2. In fact, we can have up to k for some fixed k. And so that's why it's a generalized version of the bipartite branching program. All the other parameters remain the same. Now, it actually turns out that generalized bipartite branching programs can be simulated by a bipartite. It can be turned into a bipartite branching program just by increasing the size by a quadratic factor. And then we could actually show that this generalized version of bipartite branching program characterizes memoryless communication complexity. And the way it works is we can look at every message of the memoryless communication complexity that the players send. And in a sense, it acts as a node in the generalized bipartite branching program. So using this fact, we can say that we can say that memoryless communication complexity is actually characterized by bipartite branching programs. Okay. Finally, let me say another connection, which is of this newly defined memoryless communication complexity with formula size. So it was already known from the work of Clark and SP from 2014 that any formula of size S containing arbitrary fan-in-2 gates can be converted into a garden hose protocol of almost the same size. So of size S to the 1 plus epsilon for any arbitrary epsilon. Now, in this work, we are showing that any arbitrary garden hose formulas can be simulated by a memoryless protocol without any loss, in the sense that if we start with a S size garden hose protocol, then we get a log S size memoryless protocol. So S becomes log S here. So using these two results, we can say that given any formula of arbitrary fan-in-2 of size S can be converted into a memoryless protocol of size 1 plus epsilon log S. Now, in the contrapositive direction, this says that this new model of memoryless communication complexity actually gives us a way of proving formula size lower bound, because so any lower bound in this model would actually translate to the formula size lower bound. So in its nature, this is similar to the result of Customers and Witterson. So here we have this form of communication complexity, where just by analyzing communication complexity, we can actually show a lower bound for formula size. Okay, but I should highlight here that in this model, in the memoryless model, constants really matter, in the sense that here a log n and 2 log n shouldn't be treated as equal, because a log n bound in the memoryless model would actually translate to n lower bound in the formula size, whereas 2 log n would actually translate to n squared lower bound. So constants really matter here. Okay, and at last, I want to mention that we also defined a quantum version of all the variants of memoryless communication complexity model. And we managed to show that the quantum versions are actually exponentially better than their classical counterpart for explicit functions. So we could find different functions for which this inequalities are exponentially weaker, except this one. So we couldn't do it for the uh, memoryless model. For the other variants, we could find it. Okay, finally, let me stop with one main open question. So I have already said this in a sense. So note that uh, we know that if we have, so we made this connection from memoryless communication complexity to garden hose to branching programs to formula sizes, and we also see that proving a lower bound here would actually give a lower bound in all these different models. So what we could do is we could prove a lower bound for c equal to 1. So in this model, we could prove a lower bound of log n, but we couldn't prove any lower bound yet, which is greater than equal to 1. So which is greater than 1, strictly greater than 1. And in particular, a such bound of greater than 1 would actually have consequences in first of all in Gardner's model, because if we could prove c strictly greater than 1, then that would prove a superlinear lower bound for Gardner's, which is actually open. And this would also give a lower bound for bipartite branching programs. So if we could prove like C for any C, the C log n bound that we prove, we would actually give n to the C lower bound for the bipartite branching program. And this is similar in flavor of Tal's recent work on bipartite formula size lower bounds. So here we are getting bipartite branching programs lower bound. And also note that if we manage to prove C to be greater than 2 plus epsilon, so then that would have a really nice consequence of having omega n to the 2 plus epsilon lower bound for the general formula size, and which is actually open from the best we know from Nechiporuk from 1966. And one possible candidate that we think is viable is this three-click problem. Here, Alice and Bob are given two strings x and y, and if we take x XOR y, so then this XORed string would actually represent a graph. And then the question is whether this graph, an n-vertex graph, and then the question is whether this graph would contains a triangle or not. And it seems like for this problem, it cannot be done with log n in memoryless communication complexity. Okay, so with that, I'll stop here. Thank you for listening, and you can visit this link for the full version of this paper. Thank you.